So there you go. So now let's play around with it. So what I wanted to do is introduce you to it. A lot of the stuff that I'll do in class, by the way, we're going to do a lot of board work, and then we'll do a lot of MATLAB. Okay? All your homework is going to be MATLAB. Now, some of you may be nervous about MATLAB. Let me start at the computer here before we talk about your nervousness about MATLAB. Some of you are already MATLAB superstars. Right? Am I right? Who's a MATLAB superstar in this room? Don't be shy. Oh, yeah. Okay, so I know a bunch of people took 581 from me, and if you didn't raise your hand, that was really embarrassing for me. Because the whole point is I was making you a MATLAB superstar, and then now you're telling me you're not. So embarrassing. Anyway, there are some MATLAB superstars. Maybe you guys are just being shy. But I'm going to make you into a MATLAB superstar by the end of this class. And don't worry, all the codes are in the notes, and you just build from there. Okay? We're going to start slow, keep going up. The beautiful thing about MATLAB is it has very high-level programming languages. It's a very high-level language, so it's kind of very simple commands that do a lot of work for you. Let's try this. This is the first day. See, the first day is when things always go. There we go. Okay. Or can go wrong. Zach, that floor comfortable for you? Awesome. Okay, good. Okay, you probably won't have to sit there for the next lecture. There's a chair right there, too, by the way, if you want to take that. Okay, so MATLAB, we're going to open it up. We're going to program in it. I want to make sure that you guys see my screen on the back TV there versus seeing me. Okay, so, all right, so let's first pop this open. We're almost there. And perfect. Okay. Can we have the lights down in front and make sure, do you guys see that on the back screen there? Okay, great. Okay. All right. Just in case you don't know how to start MATLAB, you look at the MATLAB icon, there it is, see right there, and you push it twice really fast. Okay, there we go. See, you're already getting on your path to success in life. Pretty much success in life is equated with MATLAB skills. I don't know if I haven't written a paper up yet on that, but I'm pretty sure I will. Could we do the lights down in front? Lights out in front. Thank you. Okay, so here we are. Here's our little platform for MATLAB. And, what I'm going to do is I'm going to take a Gaussian function, and I'm going to Fourier transform it. And it turns out the Fourier transform of a Gaussian is another Gaussian. So we're going to just play around with what the Fourier transform does. It's very important that you understand what fast Fourier transform does. So let's open a new file. File, new. Okay, good. There it is. And come on. Where are you? There you go. Okay. Do that. Okay. I want to bring this into size. Jeez, how come it's not? There we go. Okay. All right, so I always start my codes with the following commands. Not everybody does, but clear all, close all, CLC. It means you get a fresh start in life right there. If you don't do that, you're not guaranteed a fresh start. Your past sins can be held against you. But not me. As long as I have that in my code, I know I start off square zero. Okay? So there we go. That's just the clear all, by the way, removes all variables that have ever been defined. Sorry, that's what clear all does, yeah? Close all shuts down all the figures. Don't underestimate the power of how much a figure eats up your CPU. Don't leave figures open. Okay? And CLC, it clears this little screen here. So for instance, you might have junk left over from last time you made a mistake. And you got, when I ran it, did it just create that, or was that from last time? You know what? When you got that CLC command in there, you know it's from this time. Okay? So you're not trying to debug something that you fixed. Okay? All right. So let's make a function up. I'm going to define a domain, 20. I'm going to break it up into 128 points, because that is a power of 2. Good? And I'm going to define x2 as a linear space. And don't worry, you guys are going to get good at these commands, and some of you already know them. And if you don't, you will get to know them very well, very quickly. So the linspace command does is it creates a linear space. It goes from negative L over 2 to L over 2 in n plus 1 points. Now, why n plus 1 points? Am I not chopping this up at n points? Well, it turns out, remember, Fourier transform assumes things are periodic. So the last point is the same as the first. They're redundant points. But the last point exists. You want n points, and the last one is the n plus first point. So I'm going to define all n plus 1 points that start on the left, hit the right, and then what I really want are just the first 1 through n points. X. That's the x I'm going to work with. This is my spatial domain, my f of x. The first 1 through n points. So I threw away the last point. I can do that. By the way, I can do anything. It's my code, right? You can't stop me. I can make mistakes. You can't stop me. Okay? I throw away the last point because it's the same as the first. It's redundant. Okay, good. And now I'm going to define a function. U is equal to, we'll just make a little Gaussian here. There it is. And we're going to plot it. Plot x versus u. Ready? Boom. Oh, yeah. So let's call this winner 12. Hey, math. Okay, good enough. And look at that. I just plotted a Gaussian. Now, the Fourier transform of this Gaussian looks like another Gaussian. So I'm going to Fourier transform it, and you're going to see this. Ready? You guys all ready for that? Okay, here we go. We're going to Fourier transform this. UT, FFT, U. I told you it was that easy. Okay? So now what we're going to do is we're going to just plot that. So first, go like that, boom, and whoa. Does that look like a Gaussian to anybody? Wow, thanks, Charles. All right, I was just thinking maybe you guys are trying to, I can make it look like a Gaussian. I can make it. Willpower. All right, what happened? Because it's supposed to be a Gaussian. Now, remember, you asked a question about gluing this thing back together. When you take this function, you keep breaking it into smaller pieces, and then you try to glue it back together, there's a certain algorithm to do this. It's a butterfly algorithm, the way it patches back together. But it takes work to patch it back together because it naturally wants to be in the butterfly form. And what the butterfly form does is when you Fourier transform something, this happens. Ready? Here's my Gaussian. Boom. Cut it in half in the middle. Flips sides. Multiplies every other component by -1. So now try to picture the Gaussian. Flip sides, multiply every one by -1. Can you see it? Okay, all right. This is like a Rochet test. Well, not quite. So what I'm going to do to shift it is use the FFT shift command. It knows it's using the FFT. If you really want to look at it, the spectral content, you do FFT shift. And that shifts it back. And then not only that, we're going to look at the absolute value of it. That'll change my -1s to 1s. Okay. And then we run that. And look at that. There is our Gaussian. Okay? So that's the frequency content. Now, let's talk about what's supposed to be going on down here. What is this axis? I didn't plot an axis. Did you see what I did? I just said plot U of t, absolute value, FFT shifted. I didn't tell you what this was. So right now, since I didn't put an x-axis, it's 128 points in that, right? So it's just 0.1, 2, 3, 4, 5, 6, all the way up to 128. But what is this axis supposed to be? This is supposed to be our frequencies. We went from the x domain to the frequency domain. These are supposed to be frequencies. So here's how you define this. And I'm going to tell you, they're the k, the wave numbers, k. So these are like my frequency content. Okay? It's going to be what it is. And I'm going to show you this first, and then we'll talk about it. Okay, what is that? Because I'm going to plot this, k versus that, and make sure I got it right. I'm pretty sure I did, but it's always good to check. Yeah, okay, there it is. So what is this k? So first of all, let's talk about the pieces that are in there. There's a 2 pi over L. MATLAB thinks you are working on a 2 pi periodic domain. That's what it assumes, okay? By the way, we're not, are we? What was our domain size? 20. Now, I don't want to plot a Gaussian on 2 pi. I want to work with 20. I want to do what I want to do, okay? But MATLAB thinks we're working on 2 pi. So what this 2 pi over L is simply telling it to rescale. Look, you're thinking 2 pi, I'm thinking L. Let's make this work out. There it is. Reshifts it. It's basically a normalization, change of variables in the MATLAB way, and you've done it with the 2 pi over L. Okay? So now it believes, oh, yeah, you're working with 2 pi. I'm working with 2 pi. We're all good. What this is then the frequency numbers. Cosine 1x, cosine 2x, cosine 3x. These are just integers telling me cosine 1, cosine 2x, cosine 3x, okay? That's what these are. But why did I do this crazy shift? Because my FFT got shifted, right? Because the FFT does this, my frequency numbers have to do that, okay? So when I plot this, so remember, when we work in this domain, when we're in the Fourier domain, this U of t domain, everything is shifted. So the k has to account for that. So the k is shifted too. So when I plot here, I don't want to plot k. I want to plot the shift of k as well. Okay? So what I do is say FFT shift of k. And I can run that. Here it is. This is now the plot I want. This is the spectral content of that Gaussian. It's a Gaussian, and what you see here, this is like cosine 0x, cosine 1x, cosine 2x, cosine 3x, all across here. I have 128 points defining the spectral content of that signal, or that whatever object it is. Okay? I just took the thing from the time domain or the x domain and I converted it into frequency content. And what these are, this represents the A of n's and B of n's if you'd like. Okay? The coefficient of how much energy is at cosine 0x. That much. Okay? So it tells you the strength of all the frequency content. That's what this does. Okay? Everybody good with that? And all I did, FFT.